Okay, so we're going to look at the multiplication rule, and we're going to do this by looking at example 1.7.1 from the group. So to get started, you're going to look at the image below, and in the image, you'll see A, B, and C. And A, B, and C represent three different locations. In between A, B, and C, you're going to see some curves of a circle, also some lines that are numbered. And each of those numbered lines and curves represents a different route from A, B, and C. So if you look carefully, you can see that there are three routes from A to B. And just to make it clear, I will circle the routes. So here's 1, 2, 3. And that's how we got the three routes here. And from B to C, there are 5 routes. So that's 1, 2, 3, 4, 5. So the question is, how many routes are there from A to C? So to solve this, we can multiply the number of routes from A to B by the number of routes from B to C. So from A to B, we got 3, and for B to C, we got 5. So 3 times 5 is 15, which tells me that there's 15 routes from A to C. In case this doesn't make sense, I wrote out all the possible routes that you can take to get from A to C. So in orange, we have 1, 4, 1, 5, 1, 6, 1, 7, 1, 8. Next, we have 2, 4, 2, 5, 2, 6, 2, 7, 2, 8. Following that, we have 3, 4, 3, 5, 3, 6, 3, 7, 3, 8. And so if you count up all the orange options, all the yellow, and all the blue, that's a total of 15 different routes. Now we are going to look at another example. This is example 1.7.3. So we have 2 die rolled. What's the total number of outcomes? So for die 1, remember that a dice has 6 sides. So there's 6 possible options. So you have 1, 2, 3, 4, 5, 6. So there's 6 outcomes there. And for die 2, same thing. Your options are 1, 2, 3, 4, 5, 6. That gives you a total of 6 outcomes. So using the multiplication rule, you're going to multiply the number of outcomes with each other. So 6 times 6 equals 36. So that tells me that we have 36 outcomes. In case you can't see how the multiplication rule is helping us here, I will draw out a chart to help you. So I've already pre-drawn this chart. And up top, we're looking at die 1, and I labeled die 1 in black. So each of the numbers 1, 2, 3, 4, 5, 6 in this row right here, they represent all the possible options for die 1. And then on the y-axis, I have die 2 in yellow, and all the options for die 2 are written in yellow. So we have 1, 2, 3, 4, 5, 6. Okay. Then in the middle of the table, what I've done is I've combined the option for die 1 with the option for die 2. So for example, in the first box, if die 1, the first time you rolled it, you got a 1, you write 1 in this box right here. And then for this second die, when you rolled it, you got a 1, your final outcome would be 1, 1. So that's basically how I filled out the whole entire table. And if you count each of the little boxes that are inside this chart, you will see that there's a total of 36 little boxes. And that's the same thing as 36 outcomes. Okay, so now we're going to look at theorem 1.7.2. So an experiment has k parts, or steps, where k is greater than or equal to 2, and the ith part of the experiment can have ni possible outcomes, where I equals 1, 2, 3, all the way to k. Okay, so that's just the first part of the theorem. So to make sure that you understand what's going on, I've written out in green, yellow, and blue parts of this theorem, okay? So we're looking at an experiment, okay? And experiment does not necessarily refer to science experiment, okay? So it can mean that you're going to do some sort of task, okay? And in the theorem it says an experiment has k parts, okay? So in yellow, I wrote out all the parts, 1, 2, 3, 4, all the way to k, right here. Okay? And the parts are like, can also be looked at as steps of the experiment. Okay? And an important thing is that k has to be greater than or equal to 2, which is why I have more than 2 parts to my experiment. Okay? And it says, the ith part of the experiment can have ni possible outcomes where I equals 1 all the way to k. So the first thing I noted when I read that was that, okay, part 1 is basically I equals 1. Part 2 is I equals 2. Part 3 is I equals 3. And part k down here is I equals k. Okay? So each of these parts in yellow right here have an outcome, and their outcome is ni. So for part 1, its outcome is going to be n1. Part 2, the outcome will be n2. Okay, and you just keep going like that. So for part k, your outcome is going to be n sub k. Okay, so I'm going to continue reading the theorem. So it says, okay, I'll start from the top just so that everything's all together. So it says, an experiment has k parts where k is greater than or equal to 2. The ith part of the experiment can have ni possible outcomes, where I equals 1 all the way to k, and that all the outcomes in each part can occur regardless of which specific parts have occurred in other parts. To figure out the total number of ways this experiment can occur, we can multiply the number of outcomes for each part. So they said that we can multiply all the ni's from each of the parts together to figure out the total number of outcomes. So written below, I have the format of what this should look like, okay? So right here you see a pi sign. This pi sign is not the regular pi symbol where it's like 3.14. That's not what it stands for, okay? When you see this capital pi sign like this, that tells you that you're dealing with multiplication. It's kind of like the summation sign, like this, where we use to sum things up. But here we're using capital pi to indicate multiplication, okay? So you're multiplying the ni's from I equals 1 all the way to k. So when I expanded this left side right here, you can see that on the right side right here, what we're doing is we're multiplying all the outcomes. So we're multiplying n1 times n2 times n3 times n4 all the way until we get to nk. So now we're going to look at an example that uses the previous theorem that we just looked at. So the example says, create a password with 8 characters, 4 numbers followed by 4 letters. You can reuse the numbers and letters. What's the number of ways you can construct this password? So in the problem, since it says that our password can have 8 characters, I drew out 8 little black lines. So each of these lines represents a part/step of the experiment. And for this problem, our experiment is creating a password. So the first 4 spots are going to be numbers. And the last 4 spots are going to be letters. So to figure out the number of options we have for each of our outcomes, n1, n2, n3, n4, n5, n6, n7, and 8, I'm going to do the following. So first I'm going to figure out how many options I have for the numbers. So for the numbers, I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I count all those digits, that gives me a total of 10 options. And since I'm allowed to reuse the numbers, I know that I have 10 options for N1, 10 for N2, 10 for N3, 10 for N4. The next thing we're going to look at is the letters. So for our alphabet, we have 26 letters, and I know that I can reuse the letters. So that tells me that for N5, I have 26 options, N6, 26, N7, 26, and N8 is also 26. So using the theorem that we learned on the previous page, I'm going to take the product of all of our outcomes Ni. And so what I'm going to do is I'm going to take the product of Ni from I equals 1 to 8. So how do I know that I go to 8? I know that I go to 8 because our password requires 8 characters. Okay, so when I expand this right here, I'm going to get N1 times N2 times N3 times N4 times N5 times N6 times N7 times N8. And then I can plug in the appropriate numbers. So N1, N2, N3, and N4 is 10 for each of them. So I'm going to do 10 times 10 times 10 times 10. N5, N6, N7, and N8 are each 26. So I'm going to do times 26 times 26 times 26 times 26. So when I multiply out all these numbers, I'm going to get this number right here. And this number right here is my answer. And that's the number of ways that I can construct the password. Okay, so here we have another example. It says, create a password with 8 characters, 4 numbers followed by 4 letters. You cannot reuse letters or numbers. How many possible ways can you construct this password? Okay, so since it says that I can use 8 characters, I'm going to draw 8 lines. And then it says I can have 4 numbers first, so it's these 4, followed by 4 letters, these 4. And then it's telling me that I cannot reuse letters or numbers. Okay, so to figure out my options for numbers, I'm just going to start listing off the numbers. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you count up those digits, that gives you a total of 10 options. So if we start with the first option, I know that I can have 10 possible options, okay? But then, since it says that I cannot reuse letters, that means if I use one letter, I'm down to 9 options. If I use up 2 letters, I'm down to 8 options. If I use up 3 letters, I'm down to 7 options. Okay, and then for letters, we know that we have 26 options. And for this spot right here, I'm going to have 26 options possible. Then I use one letter, I'm going to only have 25. Then 24, 23. Okay, then using the theorem, and take the product of the ni's. So this is n1, n2, n3, n4, n5, n6, n7, n8. So it's going to be product of ni's from I equals 1 all the way to 8 equals n1 times n2 times n3 times n4 times n5 times n6 times n7 times n8. And that's going to equal 10 times 9 times 8 times 7. Okay, followed by multiplying times 26 times 25 times 24 times 23. Okay? And then when you go ahead and multiply out these numbers, that will give you the number of possible ways that you can construct the password. You can either multiply out these numbers or you can leave it in this format if your teacher allows you to. Okay, so now we're going to look at permutations. So for permutation, order matters, okay? And the formula for permutations is P subscript n comma k, where n represents the number of objects and k represents the number of spots to fill with order mattering, okay? And that's equal to n factorial over n minus k factorial. So note that factorials are only used for discrete whole numbers, like 0, 1, 2, 3, 4, 5, 6, 7, 8, etc., okay? And then these are some important things to keep in mind. So n factorial equals n times n minus 1 times n minus 2 times n minus 3, all the way until you get to times 2 times 1. And 1 factorial equals 1, and 0 factorial equals 1. So I'm just going to give a quick example of what a factorial looks like when you solve it. So if you have 3 factorial, that's going to be 3 times 2 times 1, which equals 6. Okay, so now we're going to look at an example. So it says, there are 25 club members. The club needs to pick a president and a vice president. How many ways can we fill these two positions? So the first thing I did was I drew out 2 lines to represent the 2 positions, okay? So we need a president, P, and we need a vice president. So I'm going to put V. Okay, so for president, we have 25 options because there's 25 club members. But if we use 1 person for president, that means we're only going to have 24 options for vice president. Okay, so with this information, I can use the theorem that we learned earlier, and I can just multiply 25 times 24, and that gives me 600. So that means that there's 600 ways that we can fill these 2 positions. Okay, so we can also use a permutation to solve this problem. And how do I know this? Okay, so in the problem, I know that the objects were the members, okay? And so objects we represent by the symbol n, okay? So n equals 25. And the spots to fill were president and vice president. And I know that the symbol for spots to fill is k, and president and vice president, that's 2 positions, so k equals 2. Okay, so I know that the order matters for these spots because if I have 25 options for president, then I have 24 options for vice president, or vice versa. Meaning, if I have 25 options for vice president, that means I only have 24 options for president. Basically, when you are dealing with a situation without replacement, you are dealing with a permutation. So the key takeaway is when you're dealing with without replacement, that means you're probably dealing with a permutation. Okay? So now we're going to use the permutation formula, which is P n comma k equals n factorial over n minus k factorial. If we plug in the values for n and k, n is 25, k is 2, we have P 25 comma 2 equals 25 factorial over 25 minus 2 factorial. Simplify it, we get 25 factorial over 23 factorial. Simplify it further, we get 25 times 24 times 23 factorial divided by 23 factorial. And since we have 23 factorial on top and bottom, we can cross those out. And we get 25 times 24, which gives us 600. So that tells me, just like the previous steps we used, we get 600 here, and we got 600 here. So there are 600 ways that you can pick a president and vice president. Here's another permutation example. So you have 6 books that need to be arranged on a shelf. How many ways can you arrange the books? Okay, so 6 books, that's the number of objects, so n equals 6. And the number of spots that I need to fill is also 6, so k equals 6. So if I use permutation, I have p 6 comma 6. So I have 6 factorial over 6 minus 6 factorial, and that gives me 6 factorial over 0 factorial, simplifies to 6 factorial over 1, which equals 6 times 5 times 4 times 3 times 2 times 1. Again, the reason why I knew that this was a permutation problem was because I knew that order mattered, because I knew that the first spot could have 6 options, right here. But then, once I used up one of the books, I would only have 5 options for the second spot. And if I used up, this represents one book, this is the second book, the third spot would only have 4 options. And then if I used up 3 books, which are represented by the arrow, so 1, 2, 3, that means I'd only have 3 options for the fourth spot, 2 options for the fifth spot, and then only 1 option for the last spot. Sampling with replacement. So you can find the total number of outcomes by using n to the k, where n equals the number of objects per spot, and the number of objects n is the same for each spot, and k equals the spots to fill. Okay, so now we're going to look at an example. So it says, flip a coin 3 times. How many ways are there to get 3 coin flips? So the first thing I figured out was the number of objects per spot. So I put down n equals 2. And I'll share my reasoning for how I figured that out. So a coin has heads or tails. Heads is one option and tails is one option. Heads and tails is a possibility for each flip. This is why n equals 2, because each flip has 2 possibilities. Since the exact options are available for each flip, it is basically like we are dealing with a replacement scenario. Okay, and then I knew that k was equal to 3 because we were flipping the coin 3 times. So I used the formula n raised to the power of k, and since I knew that n was equal to 2 and k was equal to 3, I did 2 raised to the third power, which equals 8. That told me that there's 8 ways to get 3 coin flips. Okay, if you don't believe me, you can manually write out the options that you would get. So that's what I did below. So for example, if I got heads, 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 then heads, heads, tails, heads, tail, tails, heads, tail, heads, tails, 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 heads, tails, heads, heads, and tails, heads, tails. Those are the total possible ways that I could have flipped the 3 coins. And if you count up the total number of options, that's also 8. Okay, so now we're going to look at the birthday example problems. So the first one is, how many ways are there to have birthday assignments to 20 students? Okay, so n equals 365. And remember, n is the number of objects for each spot. So I knew that it was 365 because there's 365 days in a year. And then for k equals 20 because I have 20 students. And that's like the number of spots I need to fill. So using what we learned, I put n raised to the power of k, which is 365 raised to the power of 20, and that's the number of ways that I have to assign birthday assignments for 20 students. Okay, problem 2, it says, how many ways are there to assign birthdays if no one shares the same birthday amongst the 23 students? So here's my approach. Since no one shares the same birthday, this problem looks like a without replacement problem, which means that we are dealing with a permutation. So n equals 365, and k equals 23, with order mattering since no one can have the same birthday. So I just plugged it into the permutation formula, p of 365, 23, which equals 365 factorial over 365 minus 23 factorial, which is equal to 365 factorial over 342 factorial. And if you simplify, you're going to get 365 times 364 times 363 all the way until you get to times 343. Ways of assigning birthdays when no one shares the same birthday. Okay, problem 3 is, the class has 22 students. What is the probability that at least 2 of them share the same birthday? So let's think about what we want, okay? So we want the probability that at least 2 share the same birthday. So our event here is A, and A equals at least 2 share the same birthday. And a complement is no one share the same birthday. So remember that we learned earlier that the probability of A is equal to 1 minus the probability of A complement. Okay, so I know that the probability of A complement is the probability that no one shares the same birthday. So how do we figure that out? Okay, well, we can use a fraction to help us figure out the probability that no one shares the same birthday, okay? So the numerator is going to be the number of ways no one shares the same birthday. and the denominator is the number of ways people, there's a little mistake, people can have a birthday. Okay, so for the numerator, since we're looking at ways that no one shares the same birthday, that means we're dealing with a situation without replacement. And without replacement tells me, okay, I'm dealing with permutation. Okay? And for the denominator, I know that we're looking at the total number of ways that people can have birthdays. So that means some people can have birthdays on the same day, which means we can have replacement. So we're going to have n raised to the power of k. So putting all the information together, I know that the probability of a complement equals permutation on top, which is p n comma k, divided by n raised to the power of k. And I know that n equals 365 because that's the number of options I have, and then k equals 22, which is the spots I need to fill. Okay, so I have permutation of 365 comma 22 divided by 365 raised to the power of 22. And then I'm going to use the probability equation we came up with earlier, which is probability of A equals 1 minus probability of A complement. Okay, and remember that A represents at least 2 share the same birthday. Okay, so we have 1 minus probability of A complement. We plug in the probability of A complement, so we get 1 minus P, which is permutation, 365 comma 22 divided by 365 raised to the power of 22, and our answer turns out to be 0.476, so about 0.5. So for combinations, order does not matter. And the formula we use is C n comma k, again where n is dealing with our objects, k is spots to fill, equals n choose k. So whenever you see n over k like this, that means n choose k. Okay, and that's equal to n factorial over k factorial times n minus k factorial. Okay, so now we're going to look at the difference between permutation and combination. So for permutation, remember order matters, and combination, order does not matter. Okay, so we have AB and BA. For permutation, it's going to be 2 separate options. But for a combination, if we have AB and BA, it's considered as one option because order does not matter. So it's basically like AB equals BA. Okay, so here we're looking at an example. It says select 8 people from a group of 20 for a team. Order does not matter. How many ways can you do this? Since order does not matter, this is a combination problem. So n equals 20 and k equals 8. Okay, so how do I know this? So I know that I want to pick 8 people, so that's like 8 spots. And I know that I have 20 options, so that's like 20 objects, which is why I put n equals 20. Okay, so then, since this is a combination problem, I'm going to write C 20 comma 8 equals 20 choose 8, which equals 20 factorial over 8 factorial times 20 minus 8 factorial, which simplifies to 20 factorial over 8 factorial times 12 factorial. Okay, and you can simplify that further, but if your teacher allows you to, you can leave your answer like this. Example, select 8 people from a group of 20 for a team. Each person must have a different task. How many ways can you do this? Okay, so since the problem states that each person must have a different task, I know that we are dealing with a permutation problem since order matters. So we have n equals 20, k equals 8. Plug that into our permutation formula and you get 20 factorial over 12 factorial.